Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Welcome to this explainer, where we're diving into one of the absolute most fascinating and frankly elusive molecules in all of chemistry, dicarbon. You know carbon, right? It's the bedrock of life, it's the graphite in your pencil, the diamond in a jeweler's case. But when carbon tries to pair up with just one single other carbon atom, things get incredibly strange.
Think about it. This is the core paradox we're unpacking today. Carbon is literally the foundation of our entire material world. Yet, C2, or dicarbon, simply cannot exist in a stable, free state under standard everyday conditions. It's this kinetically transient, highly endothermic ghost of a molecule.
Okay, let's quickly run through our roadmap for solving this mystery. We're going to hit 1. The enigma of dicarbon, 2. Thermodynamics and kinetic reactivity, 3. The quadruple bond puzzle, 4. Quantum and classical mechanics, and finally, 5. Spectroscopy and organometallic synthesis.
All right, jumping right into Section 1, the enigma of dicarbon.
You know, the famous swan bands were driving scientists absolutely crazy long before we had the quantum mechanics to actually understand them. William Wollaston first spotted these optical emissions in a glowing hydrocarbon flame way back in 1802. They were a total mystery. It wasn't until the early 20th century that scientists finally definitively assigned that signature green spectral glow to neutral homonuclear diatomic carbon.
So here's the deal. You are never going to find free C2 just floating around your living room. Why? Because it instantly condenses into soot or solid carbon networks. But if you look at high-temperature, high-energy environments, like the glowing green coma of a comet, the atmosphere of a carbon star, or the extreme heat of a shock tube detonation, that is exactly where C2 thrives as a free molecule.
Let's move on to Section 2, thermodynamics and kinetic reactivity.
Just take a second to wrap your head around this number, positive 828.33 kilojoules per mole. That is the standard enthalpy of formation required to vaporize solid graphite into gas-phase dicarbon at room temperature. It's a truly staggering energy penalty. You're basically trying to rip apart this beautifully stable two-dimensional pi-conjugated network of graphite sheets, which nature strongly prefers to keep intact. When you stack these binding energies up against each other, the math is just undeniable. An isolated C2 molecule has about 301.4 kilojoules per mole of binding energy per carbon atom. But in graphite, that jumps all the way up to 716.7 kilojoules per mole per atom, complete with infinite resonance stabilization. So you can instantly see why the dimerization of C2 back into solid graphite is so violently exothermic. Carbon wants to be in a lattice. It definitely doesn't want to be isolated in a pair.
And here's the real kicker. Even if you miraculously manage to create C2, it faces what chemists call barrierless autopolymerization. Basically, if one C2 molecule bumps into another, the activation energy for them to react is zero. None. They react at the absolute gas kinetic collision limit, rapidly ballooning into C4, then C6, and almost instantly condensing into soot or nanostructures. In condensed media, it's just kinetically doomed.
Which brings us to Section 3, the quadruple bond puzzle. Okay, looking at the canonical molecular orbital configuration for this molecule, standard theory suggests something just bizarre. We've got 8 valence electrons. 2 go into a bonding sigma orbital, but they're immediately canceled out by 2 dropping into an anti-bonding sigma orbital. The remaining 4 fill up the pi bonding orbitals. So basic qualitative MO theory tells us C2 has 2 pure pi bonds, but 0 net sigma bonds.
Having a stable diatomic molecule without a formal single sigma bond framework is a truly wild architectural anomaly.
Because those bonding and antibonding orbitals are sitting so incredibly close together in energy, your basic single determinant models just completely fall apart. This gives C2 a really strong multi-reference character. To actually capture reality here, quantum chemists have to use advanced multi-configuration calculations. They're essentially mathematically promoting electrons from the antibonding orbital up to a higher unoccupied bonding orbital, just to stabilize the math and restore a little bit of that sigma bonding character.
To make sense of the molecule's surprisingly tight bond distance and high force constant, Sasson-Scheik and his colleagues threw a massive curveball into the chemistry world in 2012. They proposed a highly controversial quadruple bond model. It features a traditional central sigma bond, 2 pi bonds, and then this wild fourth inverted sigma bond. The orbitals for this fourth bond point outwards on the backsides of the carbon atoms and literally bend around the outside of the nuclei to overlap. It adds about 50 to 70 kilojoules per mole of stability. Let's dig even deeper in Section 4, Quantum and Classical Mechanics. This is where it gets really fascinating. At room temperature, C2 doesn't even bother existing in just one state. The energy gap between its singlet ground state and its lowest triplet state is exceptionally tiny, only about 7.3 kilojoules per mole. Because that gap is so incredibly small, any C2 existing above 300 Kelvin is actually a thermal mixture of both singlet and triplet states at the exact same time. So to map out how this molecule stretches and spins, scientists historically leaned on the Dunham double power series. Introduced back in 1932, it uses a semiclassical approximation to solve the Schrödinger equation. This spits out a massive empirical potential expansion, using spectroscopic coefficients to help us understand C2's vibrational and rotational dynamics. But there's another approach, the Rydberg-Klein-Reis, or RKR method, which derives turning points directly from experimental energies. Now, in a truly beautiful moment of mathematical unity in 1962, a scientist named Hurley proved that these two drastically different methods, the Dunham expansion and the RKR inversion, are actually mathematically identical near the molecule's equilibrium point. Fast forward to 2021, and thanks to modern pre-dissociation dynamics, where scientists literally rip the molecule apart with lasers using velocity map imaging, we finally nailed down this incredibly precise bond dissociation energy. Schmidt and his team locked it in at exactly 602.804 kilojoules per mole. Getting that level of precision puts our understanding of C2 right on par with deeply studied molecules like nitrogen and oxygen. Finally, let's wrap things up with Section 5, Spectroscopy and Organometallic Synthesis. Because homonuclear C2 is perfectly symmetrical, it has absolutely no permanent electric dipole moment. That means it's basically a ghost, completely invisible to the standard microwave and infrared scans used by astronomers. So to hunt it down, they have to look for very specific electronic transitions, the visible swan bands in comets, the near-infrared Phillips system in interstellar clouds, and the ultraviolet Mulliken system for laser probing right in the lab. But this trapping method is a true testament to human ingenuity. Since we know free C2 autopolymerizes in a heartbeat, chemists figured out how to pin the frantic molecule down between strongly donating Lewis bases, things like N-heterocyclic carbines or bulky phosphine ligands. By stabilizing the C2 core so it acts as an electron-rich ligand, we can finally tame it in a laboratory setting for advanced catalytic research, entirely bypassing its thermodynamic curse. I want to leave you with this thought today. We have tracked C2 from the glowing tails of comets all the way down to the deepest quantum models of its controversial quadruple bond. We understand exactly why it can't survive naturally on Earth, and we've finally learned how to trap it. But what happens when we eventually harness its immense reactive power at scale? Unlocking the missing link of carbon chemistry might just be the key to synthetic molecular architectures we haven't even dreamed of yet.
Like what you shared.
This website makes learning so easy. I found all my resources here.
Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious mind.